In this video, we are going to understand why some substances are strong electrolytes, why some are weak, and why some are non-electrolytes. First, let's talk about ionic substances. An ionic substance is usually made out of a metal, and a good example of an ionic substance is table salt, sodium chloride. Now here's a crystal of sodium chloride. It contains chlorides that are negatively charged. So the green spheres are the chloride ions here. And you see alternating sodium ions which are positively charged. They are represented in the purple spheres here. Now when you dissolve sodium chloride in water, what happens? Let's talk about water. So you have one oxygen and two hydrogens. The oxygen end in water can attract the electrons more than the hydrogens. So when it attracts the electrons, the oxygen end is slightly negative. We represent that with a delta negative. And the hydrogens are slightly positive. So you can think of oxygen as an electrical magnet with a negative end and a positive end. Now when you dissolve sodium chloride in water, the oxygen ends, which are slightly negative, surround the positively charged ions, the sodium ions, and they start dislodging them out of the crystal. You can see that happening here. The oxygen ends, shown in red, which are negative, are attracting the purple sphere here, which is a positively charged sodium ion, and they dislodge that ion, sodium ion, into the water. So similarly, the chloride ions, which are negatively charged, the green ones here, get surrounded by the positively charged oxygen atoms, and they get dislodged out of this crystal. So eventually this crystal will disappear, and when sodium chloride dissolves, it dissociates or breaks down to produce sodium ions dissolved in water plus chloride ions dissolved in water. Now we have a very specific state to represent a substance dissolved in water. You use aqueous as the state to represent what happens, to represent a state where a substance is dissolved in water. So we are going to say sodium chloride aqueous means sodium ions, dissolved sodium ions, so sodium ion aqueous plus chloride ion in aqueous state. So any ionic substance, if it is capable of dissolving in water, it will dissolve by producing ions. And that's why ionic substances conduct electricity strongly, because there are ions in the solution and they will be strong electrolytes. Now it's very important to remember that only ionic substances that dissolve will be strong electrolytes. Only soluble ionic substances will be strong electrolytes. If they don't dissolve, they don't produce these ions. So let's talk about how do we decide which ionic substances dissolve in water and which don't. This chart is very helpful. It tells you what combination of ions dissolve in water and what combinations don't. So these are solubility guidelines for ionic compounds in water. So this chart says that any ionic compound containing nitrate ion is always soluble. There are no exceptions. So it can be paired with calcium nitrate. It can be paired with calcium to give calcium nitrate. So calcium nitrate will be soluble. So will be a magnesium nitrate. Okay, so any substance with nitrate ion will be soluble. There are no exceptions to what cation you can pair with nitrate. All cations paired with nitrate will be soluble. And so with acetates. So sodium acetate, magnesium acetate, these are all soluble in water. Now bromides and chlorides and iodides are usually soluble except there are some important exceptions, except when they are paired with silver, mercury, or lead ions. So for example, lead chloride will be insoluble because you have a chloride ion paired with an exception, lead, so that will be insoluble. But if you just have potassium chloride, now chlorides are usually soluble and potassium is not an exception, so potassium chloride will be soluble. Now can you predict whether calcium phosphate will be soluble or insoluble in water? Take some time to predict whether calcium phosphate will be soluble or insoluble. Okay, now we are dealing with phosphate ion, and from the solubility chart you can see phosphates are usually insoluble except when they are paired with these. So calcium is not in the exception. It's just a normal phosphate. So phosphates are insoluble. So calcium phosphate will be insoluble. So I hope you can make use of the solubility chart to predict which ions dissolve in water and which ionic compounds dissolve in water and which don't. Let's go back to our example. Let's go back and write a few more ionic substances dissolving in water. So suppose you have magnesium chloride. From the solubility chart, you can tell that magnesium chloride dissolves in water. So when it dissolves, you can write an equation saying magnesium chloride produces magnesium ion and chloride ions. The formula for chloride is Cl negative, and you will get 2 chloride ions for every 1 magnesium chloride because there are 2 chlorines in the formula. So ionic substances dissolve by breaking down into ions. Now contrast that with molecular substances. Molecular substances, a good example for molecular substances, sucrose, table sugar, C12H22O11. Usually you identify molecular substances those that don't have metal ion, and sucrose is a molecular substance. And so is methanol, shown in this example, CH3OH, methanol. That's also a molecular substance. Now molecular substances, when they dissolve in water, they interact with water, but they do not separate out into ions. So methanol, when it dissolves in water, still remains, the carbon, hydrogens, and oxygens still remain intact. They separate from each other. They separate from each other in the bulk water. And oxygen's positive ends start interacting with the negative ends in this molecule. The oxygen in methanol is slightly negatively charged. So they interact with water, they separate from each other, but as they dissolve, they're not going to break down into carbons, hydrogens, and oxygens. So you might as well not write an equation. So aqueous methanol does not separate into ions. And that's why molecular substances do not conduct electricity. Now, these are partial charges on this molecule, but the molecule hasn't broken down into ions like in this case. These are actual ions dissolved in the solution. So a key difference between ionic substances dissolving in water and molecular substance dissolving in water is that ionic substances dissolve by breaking down into ions, whereas molecular substances dissolve without breaking down into ions. So molecular substances will be examples of non-electrolytes. They don't conduct electricity because there are no ions in the solution. Okay. Let's talk about acids and bases now. So acids are those substances which turn a blue litmus to red color. So if you put a blue litmus into an acid, it changes to red. And if you put a red litmus paper into a base, it changes to blue. That's how you can differentiate between that's how you can identify acid from a base. But what is an acid and what is a base? We can explain that taking some examples of acids and bases. Common examples of acids would be hydrochloric acid, hydrofluoric acid, nitric acid, sulfuric acid, phosphoric acid. And you can have other examples of acids. One more example I will give is acetic acid. Now, if you look at these formulas, they all have hydrogens. So let's define an acid, and we are going to use the Arrhenius definition of acid. So according to this definition, acids are substances that produce protons or H plus ions in water. So when an acid dissolves in water, so for example hydrochloric acid, when it dissolves in water, it produces, I'm going to write aqueous, dissolved in water, produces H plus ions. So it's going to break down to H plus and chloride ion. So realize that acids could be molecular substances. You see that all these are molecular substances. But if a molecular substance is an acid, it will dissolve by producing H plus or proton ions in water. So since acid dissolves by producing ions, the ions will conduct electricity through the solution. So acids will be electrolytes. Similarly, bases also will be electrolytes. And according to the Arrhenius definition, a base is a substance that produces hydroxide ions in water. So examples are sodium hydroxide, calcium hydroxide, ammonia. So you can see most of the bases have hydroxide ions, and when they dissolve in water, you're going to get hydroxide ions. So since you produce ions here as well, bases also will be electrolytes. Now within acids and bases, you can distinguish between strong electrolytes and weak electrolytes. Now strong acids, they dissociate completely into ions and they will conduct electricity strongly, so they will be strong electrolytes. This is a list of strong acids that you must be familiar with. So please memorize this list of strong acids. So if you encounter a strong acid, you must realize that it will be a strong electrolyte because it dissociates completely. What do we mean by that? So suppose you start with 100 molecules of hydrochloric acid. When you put them in water, almost all of them will dissociate. So you're gonna get 100 protons and 100 chloride ions when you dissolve 100 HCl molecules. It's a strong acid. So it's going to produce a lot of ions, and therefore strong acids will be strong electrolytes. On the other hand, weak acids, they dissociate partially, and therefore they conduct electricity weakly and will be weak electrolytes. Again, you should be familiar with these weak acids. Acetic acid is a very good example of a weak acid, and hydrofluoric acid is another example. Now let's write an equation representing acetic acid dissociating in water. So CH3COOH, when it dissolves, it produces H plus and acetate ions, CH3COO negative. But these ions are capable of combining and producing back the molecular form of acetic acid. So let's say you dissolved like 1,000 molecules of acetic acid in water. Probably only a few, one or two, will actually dissociate to give protons and acetate ions. So since you don't have many of this, since you have lots of this, lots of the molecular form of the acid and very few ions, your solution is going to conduct electricity weakly, and so weak acids will be weak electrolytes. Similarly, you should be familiar with examples of strong bases. Any group, first group hydroxide, for example, sodium hydroxide, sodium, potassium hydroxide, any first group hydroxide is a strong base. And in the second group, these hydroxides are strong bases. The rest are weak. So you should be familiar with weak bases. A classic example is ammonia. And when ammonia dissolves in water, here's the reaction for ammonia dissolving in water. We actually show it writing the water out in the equation, because ammonia is going to interact with water and it will produce ammonium and hydroxide ions. Of course, for all these you must have aqueous as the subscript because these are all dissolved in water. So ammonia is also producing hydroxide ions in water, and that's why we can call it a base, but it's a weak base. So weak, anytime you represent a weak acid reaction or a weak base reaction, notice that you have to use the double arrow. And weak bases, weak acids will be examples of weak electrolytes. Strong acids, strong bases will be examples of strong electrolytes. So remember this, any ionic compound, if it dissolves in water, will be strong electrolyte. So ionic compound, if it dissolves in water, will be strong electrolyte, if it dissolves very strongly in water. Now molecular compounds will be non-electrolytes. And molecular compounds which are acids or bases, you have to determine whether they will be strong or weak electrolytes based on whether they are strong or weak acids and bases.